So, whoops. Rebecca has asked about number 95 and 96 from the back of the book.
Chapter 8.
So let's go ahead and I'm going to zoom in on this so you guys can read it. So here's white phosphorus, and that's a three-dimensional drawing of it. And so it's 4 atoms of phosphorus bonded together into what looks like a pyramid. Okay, this reacts with chlorine to form PCl3. Write an equation for the reaction. So I'm going to zoom out a bit. And luckily, they're not asking us right now to draw a three-dimensional reaction, just write a balanced reaction. Okay, so this is number 95. We have P4 plus Cl2 makes PCl3. And we're not going to worry about the states because they don't talk about that. And I think we want to put a 4 here to get the 4 phosphorus and the 4 phosphorus here. And now we have 12 chlorine, so I'm going to put a 6 here for a balanced reaction, and that would be A. So that's pretty easy. The next one is the standard enthalpy of formation of P4 and PCl3 is given. Use these numbers to calculate the enthalpy change for this reaction. So I know I didn't give you a chance to read that very well, but I'm going to write the information down. So the enthalpy of formation for PCl3 gas is equal to minus 287.0 kilojoules per mole. And the enthalpy of formation for P4 gas is equal to plus 58.9 kilojoules per mole. Okay, and they don't give us the enthalpy of formation for Cl2 gas because presumably this is a gas, this is a gas, and this is a gas. And I'm getting that from the fact that they're given enthalpies of formation for the gases. So what is the enthalpy of formation for Cl2 gas? And the reaction looks like this. Remember, enthalpy of formation reactions are when you make exactly 1 mole of a substance in the state that you want. And when you make this 1 mole of the substance, you make it from the element in its elemental state at standard. So this is going to be a 2, and that's going to be a gas. So therefore, this is 0. So there's 100 of these that you're supposed to know enthalpies of formation, 100 plus, and they are the enthalpy of formation of any element on the periodic table in its standard state. So that means you need to know their standard states. And chlorine is a gas. Okay, so we have all that information. And remember, to get the enthalpy of the reaction using the heats of formation or enthalpy of formation, we sum the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants.
Is this the one where we have to have the coefficient of the product be 1?
For this, no, this is just for the reaction.
Okay.
Oh, you mean this? Yeah, this has to be exactly 1. So here's what I mean. For this reaction right here, it would look like this. because you're making exactly 1 mole of product. And then you have to balance this based on that. Does that answer your question about the 1?
No, keep going. We'll see.
Okay, so here, when we write this out, for the products, we have PCl3. So we're going to have 4 times the enthalpy of formation of PCl3 gas. Now, there are no other products, so I'm not going to have anything else here. That's just the end of that. And for this, when we looked at the reactants, we have P4. So 4, excuse me, there's no coefficient there, so it's a 1. 1 times the enthalpy of formation of P4 gas plus 6 times the enthalpy of formation of Cl2 gas. Okay, so when we put these numbers in here, we get 4 times negative 287.0 kilojoules. And really, this is 4 moles. So if you had 4 moles times negative 287.0 kilojoules per mole, the moles cancel out. And that's why this doesn't say kilojoules per mole. Fair enough?
Yep.
Okay, now minus, I'm not going to put the 1 in here because 1 times anything is itself. So P4 is going to be plus 58.9 kilojoules. And then plus 6 times 0. Now we can probably get a pretty good estimate of this. 4 times minus 287. Well, 287 is like 290, right? Which is really close to 300. So I'm just going to go with 300. 4 times 300 is minus 1200-ish. And really, I've overestimated by about 50. So I'm going to say minus 1150-ish. And then plus 60-ish, right?
Mm-hmm.
So my answer is going to be around negative 1100-ish kilojoules. So let's see, what did I do with my calculator? Oh, here it is. Okay, 4 times negative 287.0, I get negative 1148 kilojoules. And this is good to write here because this has 4 zig figs. And so this should only have 4 zig figs. And I'm going to subtract a negative or a 58.9 kilojoules. This is good to the 10th. This is good to the 1s. So I'm going to round to the 1s. Oh, I see when I estimated, I made that a positive and it should have been a negative. So I'm off. This should be about minus 1200-ish. And that would explain why the answer is going to be 1,206.9 kilojoules. Now, how do we write this number to there and round? We write 1207 kilojoules. So are there any questions about how to get the answer to B?
No, I'm with you there.
Okay, you good, Charlotte?
Yeah.
You're awfully quiet.
It was part C that I'm really struggling with.
Okay, so let's take a look at part C. So this is 95, part C. Based on the equation in A, determine what bonds are broken, what bonds are formed, and use this information along with enthalpy of the reaction calculated in B and bond dissociation enthalpies for phosphorus-phosphorus, chlorine-chlorine to estimate the bond dissociation enthalpy for phosphorus-chlorine bonds. Okay, so we want to estimate the bond association energies for phosphorus chlorine bonds using the bond association enthalpy for a phosphorus-phosphorus bond, the bond association energy for a chlorine-chlorine bond, and the enthalpy of reaction for the following: P4 gas plus 6 Cl2 gas gives you PCl3, and that would be 4 of them, gas. And we figured out that the enthalpy of this reaction was minus 1,207 kilojoules. So estimate the bond association energy for this using this, all of this information. So I'm going to look up the bond association energy for a phosphorus-phosphorus bond. So phosphorus-phosphorus bond is 201 kilojoules, and a chlorine-chlorine bond is 242 kilojoules. And that kind of makes sense, doesn't it? The chlorine-chlorine is bigger than the phosphorus-phosphorus.
Right.
And the reason I say that is because they're both in the same period, and the phosphorus atoms are bigger, right?
Mm-hmm.
So there's your phosphorus-phosphorus, and here's your chlorine-chlorine. So because these atoms are closer together, it's probably going to be harder to tear them apart.
Right.
Okay, so we're going to use this idea that the enthalpy of the reaction can be estimated using the sum of the bond energies of the bonds that you have to break. Usually I write broken here, but here I just wrote break. I hope that doesn't bother you too much. And here, D of the ones that you form. Okay, so that means that for this reaction, we have to have Lewis structures, don't we? Now for P4, it looks like this. And for Cl2, it looks like this. And there's 6 of these. And for PCl3, it's going to look like this. Now, I didn't count electrons yet, so I'm going to go ahead and count them. Phosphorus, which is right underneath nitrogen, has 5 electrons. Chlorine has 7. So we're talking about 26 electrons, right? 21 plus 5 is 26. And I don't care about the 4.
Why don't we care about the 4?
Because if we look at this, we really have this 4 times, right?
Right.
So how many electrons are here? 26. How many here? 26. We can build a Lewis structure for this guy, and it's going to look just like the Lewis structure for this guy.
But wouldn't you want to also put times 4 in front of it?
Well,
Just like
we'll get to that. I just want to make sure I get the Lewis structure for one of these correct first.
Okay.
So here, I'm going to have to put 2 more electrons there to get 26.
Right.
And if we look at formal charges here, we've got zeros all around. So we're really happy with this.
Mm-hmm.
Okay. Now we didn't draw lone pairs on this guy, but we're not too worried about that because they gave us the structure, right?
Right.
Okay. And this is my poor attempt at trying to draw that structure where you have 3 phosphoruses at the base. And then you got 1 phosphorus kind of at top, which all of these are connected to.
So we know there's 3 bonds.
So if we count the bonds, there's 1, 2, 3, 4, 5,
Really?
6.
Okay.
Why?
I did not assume that. I assumed there were 3. That's probably.
So again, what we're looking at is a base of 3 phosphoruses
And with the clue was when they said the like tetrahedral.
Well, actually, just the clue is the drawing. So here, let's look at that drawing. And I'm going to use a pencil here in just a moment if I can find one. Oh, there's one. So what I'm going to do here is I'm going to use my pencil and I'm going to tag each of the bonds with my pencil. And when I say tag, I'm going to draw a little line through the bond so that we know we've counted it. Okay. 1,
I mean, I can see that there's,
2, 3, 4,
6.
5, 6.
It just doesn't look like any of the ones I'm looking at in the octahedral with the 6 pairs.
Yeah, well, this is not an octahedral.
That's what I was confused about, how, I guess
mean,
it's different.
If you think about these bond angles, what are the bond angles in a triangle? And I'll show you what I mean.
Depends on
Here's a
the-
triangle. What are these bond angles? They turn out to be 60 degrees.
Yeah,
Oops, I'm sorry. You can't see what I've drawn.
in an equilateral triangle.
I'm trying to get you to read my mind. Is it working? No?
No.
Yeah, I need to practice. But you see this triangle here? That's
Right.
60 degrees.
Mm-hmm.
Have we seen a bond angle with 60 degrees before?
No.
No, we haven't. And 60 degrees is a very acute bond angle, meaning it's very small and it's not normal.
Okay.
In fact, I want you to think that normally when you have bond angles like this, the smallest we've seen is a 90 degree, right?
Mm-hmm.
Like in trigonal, bipyramidal, or octahedral, we see 90 degrees.
Right.
But more than often, we see 120 or 109.5 smooth tetrahedral, right?
Yeah.
So what does that mean about these bonds that the electrons are so close together? What does that mean?
There's more lone pairs pushing it.
Nope, it means there's a lot of strain.
So what would cause the extra strain? Because there's just in the,
What causes the extra strain is the shape in which these atoms are bonded together. Just the shape. The shape requires the extra strain. So I might be able to make this, but it would probably be tough. Let's see. So here I have this atom. And what I'm going to try and do is make a triangle, okay? Whoops, my book just fell.
oh, I see what's going on.
Okay, so here I have these two atoms, and I'm going to get another one just like it. Shoot, I don't. Actually, I have these silver ones. They'll probably work better. So these silver ones are designed to have 90-degree bond angles. Now watch what happens when I put 3 silver atoms together that are used to having 90-degree bond angles. Okay, so you can see the 90-degree bond angles, right?
Yes.
So here I'm going to do this, and then to make this work, I've got to bend it, and you can actually see the bonds are bending, right?
Yeah. Yeah.
Is that stable when the bonds are bending like that? And the answer is absolutely not.
Right.
So imagine if I put another atom up here and I do the same thing. What does that mean about this molecule with those bonds that are strained? It wants to pop apart.
They just
It wants to release that strain. So I think that this is going to actually kind of react pretty easily.
So when you have something like a hexagon, it's a lot more stable than something like that.
Like a hexagon? Do you mean an octagon?
Like I was thinking like a prism, like a,
Well, this is a hexagon,
just
and
because
these are really
more,
stable.
well, if there's more, the angle is larger.
Yeah, these angles are 120 degrees, which is totally fine.
That's what I mean. Okay.
And this is so stable that and is so flat that it's essentially a carcinogen. It can get into your DNA and make it make mistakes when it replicates. It's called benzene.
What benzene?
Okay, so let's take a look here at now the rest of this formula. So let's look at the bonds that we're breaking. We are breaking 6 phosphorus single bonds, right?
Okay.
And we are breaking 6 chlorine single bonds. And we are making, and there's a 4 out here, right?
Yeah.
1, 2, 3, 3 phosphorus chlorine single bonds, but 3 times 4 means 12 phosphorus chlorine single bonds. Okay, we know that the this amount here is given. We know this amount here is given, and we know this amount here is given. This is what we want to calculate. So what I'm going to do is I'm going to write the heat of the reaction minus 6D PP plus 6D ClCl is equal to negative 12D PCl. So what I'm trying to do here is very methodically, I'm taking this whole thing here in brackets and moving it to the other side so it
Okay.
becomes negative. Is
So
that
you
clear?
can just solve for it and just set what we
Yeah.
solved for.
And so here, if that becomes a negative and that stays a negative, I want that to be a positive, right?
Mhm.
So I'm going to put a negative here, positive here, positive here. And then finally, I get that the bond association energy for a phosphorus chlorine bond is going to be this whole side divided by 12. Okay, so I'm in good shape now to solve the riddle. So I'm going to write the bond association energy for a phosphorus chlorine bond is going to be negative 1,000, negative 1,207 kilojoules. So this one is tricky. Do you see how that the heat of reaction is negative 1,207 kilojoules?
Yeah, but it's actually positive.
But this is negative of that value. So I have to do
Mhm.
negative, negative. Are you with me?
Yeah.
Okay, so that's tricky. And then I have to do plus the bond association energy for a phosphorus bond is 201 kilojoules. For a chlorine bond, it's 242 kilojoules. And I had to put all of this over 12. So I'm going to go with my ish now. What's negative of negative 1,207?
Positive.
1,207. What's 6 times 200? Well, we can actually do this in our heads, right? It's 1,206 kilojoules.
Mm-hmm.
This one is harder to do. 6 times 240. Well, 6 times 200 is what? 1,200?
Mm-hmm.
6 times 40 is 240. So we're going to say plus 1440-ish kilojoules. And when we add these all together, you can see that you're going to get 12 plus 12 is 24, plus 14 is 38. So around 3850-ish kilojoules. And this is all divided by 12. And how many times does 12 go into 38? About 3 times. And then 250, it goes in like, 12 goes into 250 like 20 times. So 320 kilojoules. So that's about the energy to break one of those bonds.
Okay, the book said, oh, well, I guess let's see what you come up with. Maybe I'm doing my calculations slightly wrong. I'll try that
What does
again.
the book give for the answer?
326, I think. Let me double check.
Well, I
320.
expect it to be around 320, so I'm not surprised.
Oh, never mind. It says the table says 326. I'm getting confused. So yeah, when I calculated it, I got it right too.
Okay, the table says 326, but we don't expect it.
Right.
Well, actually, I should say that's not bad. I mean, if the table says 326 and we get 320-ish, I would say they're pretty much the same answer.
Mm-hmm.
So what does this tell you about this model of predicting things if it comes out pretty close to what it really is?
It's a pretty good model to
It's a
predict.
decent model. I mean, it's not perfect. What model is perfect? And the answer is, I can't think of a single model that is perfect. There's imperfections everywhere. But what models are really good for making predictions? This one is.
Okay, so what stumped me was the 6 bonds that I should have just seen from the picture.
Right, and it is kind of hard to see from the picture. But here you can see definitely you've got 3 bonds, right?
Right.
And then depending on how you put this one, you can see 1, 2, 3 more bonds. And
Yeah, I don't know why I did
this
that.
is 3-dimensional, but it's hard to see, isn't it?
Yeah, when I drew out the Lewis structure, I just only put 3 phosphoruses. So
Yeah. Sometimes people will draw this way. So that dashed line is kind of in the background.
uh-huh.
And that's how some people draw these to help them see in 3 dimensions. And here you got 1, 2, 3, 4, 5, 6 bonds.
Okay.
And this is something I do very often is when I'm counting bonds, if I'm having trouble, I will draw the darn thing out and I will count them by actually putting a line through every bond I've counted so I don't double count.
Yeah.
Or miss one.
How come we don't draw this one like a tetrahedral
This one?
geometry? Yeah.
Because it's not. You know, if you just were given P4, you would say, oh, it's phosphorus with 3 other phosphoruses attached to it, right?
Yeah.
That's what we would assume. And then you go like this. And you'd say you're done because here, actually, let me see if you would be done. No, we wouldn't like this because here, did I say 26 electrons? No, I didn't. There's only 20 electrons, right?
Right.
So this is wrong. I was thinking PCl3. So if we were predicting the geometry, we'd go with that. That's 8, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20. And this is what we'd have, right?
Right.
Now, if we don't have an octet on a terminal atom, do we have a process for getting octets on it?
Making a double or triple bond.
Okay, but where are you going to make the double bond from? You only make a double bond. You could do this. I could turn that into a double bond and it helps that guy get its octet, but how does that guy get its octet? We're not allowed to borrow electrons from a whole nother atom that's not next door. So we don't really have a process for doing this. Okay, so this is just one of those things where they did not have you try to get the Lewis structure because it's pretty impossible given the steps that they give you.
Okay.
So, but spectroscopy shows that this is the structure. So analysis using instruments shows you that this is the structure. Okay. So that's 95. I see, 95. 96, the answer does not exactly match the volume, the value of the bond, dissociated enthalpy in table 8.6. The reason is that the numbers from the table are averages, blah, 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 blah. Let's do another calculation. Do you want to do this calculation or not?
I don't think I need to.
Okay.
Now that
So
we've
how
gone-
about you, Charlotte? Do you have a question?
No, not about that.
Pardon me?
No.
Okay. Well, then if you don't have a question, then maybe we should just go ahead and do 96.
I wanted to review chapter 6.
You want to review chapter 6?
Mhm.
I think that's easy enough. When
That's
I
a good-
review chapters in this book, I just go right here.
So the last couple questions.
Chapter goals revisited.
Okay.
So you've got electromagnetic radiation. You've got Planck, Einstein energy photons, atomic line spectra Niels Bohr, wave duality, modern view of the electronic structure, shapes, electron spin, and you've got the equations that you really want to remember here.
Yeah.
And I told you I wouldn't bother with that one.
Yeah. Okay.
And the reason I wouldn't bother with that one is because this is only for a very special instance. And that's when the electron ends up in the second orbit.
Mhm.
This one is useful for any transition. So this is the one I go with.
Right.
Plus, what's the other problem with this particular equation? And the answer is very simple.
Just that it's the inverse of the
Yeah,
wavelength?
people use this to calculate the wavelength. And when you use it, you're not calculating the wavelength, you're calculating 1 over the wavelength.
Mhm.
So
There were some questions that had the energy, where energy, actually we had to use the equation Q equals MC delta T.
right, for calculating the amount
Those
of
ones were
energy
tricky.
absorbed by the eyeball.
Yeah, I mean, exactly. That was tricky.
Well,
There were like other things, like it's not only those equations is what I'm trying to point out, I guess.
right, well, that's an equation that you might want to put on your index card that says Q equals MC delta T.
And that's also like the total energy.
Well, yeah, it's the total energy absorbed by the eyeball when you take into account the specific heat capacity of an eyeball.
So when they asked for the number of photons, the Q equals MC delta T value is actually the total.
Right.
Okay.
So if you have to calculate the energy of the eyeball based on how hot the eyeball gets, you can do that.
based on the change of temperature, if we have the mass, the change of temperature, and the specific heat capacity.
Yeah. Now, honestly, your eyeball doesn't really change temperature when it absorbs energy. That's because you have this metabolic system that keeps your temperature constant.
Well, would we have a question about, like, I don't know, something that we know, like water, we know the specific heat capacity of?
Oh, sure. Water could change temperature, and that's something that would be very fair to ask, because Q equals Cm delta T. What's the specific heat capacity of water? It's 1 calorie per gram degree Celsius,
You wouldn't want us to
Or-
do the 4.18?
or 4.184
Okay.
joules per gram degree Celsius.
Okay. So is that the only kind of, that's like the weirdest one I remember.
Yeah, that's all fair game. And again, this Balmer equation is one that I would not bother memorizing or writing down, because everything you can get from the Balmer equation, you can get from these two equations, 6.4 and 6.5.
Right.
And the de Broglie-Wade equation, that's probably one that I would memorize or write down on my card, because it's one that's too easy to kind of mess up.
Mhm.
Velocity instead of frequency.
Yeah, you might mistake velocity for frequency. You might mistake M for milli, for all I know, right?
Mhm. Right.
And M is mass. So you should be able to do any one of those types of problems. Like, let's see, for the one that you were talking about with energy, I think that was from the general question area.
Number 58 is the eyeball one.
Yeah, there we go. Assume your eyes receive a signal consisting of blue light at 470 nanometers. The energy of the signal is that many joules. How many photons reach your eye? So here, you're given Q, you don't even need to calculate it, do you?
Let's see, yeah.
So how many photons reach your eye? You're going to do something like this. So this is a very useful equation. The number of photons times the energy of one photon is equal to the total energy,
Mhm.
right?
Yeah,
That's an easy one to understand.
right.
Okay, so if we're calculating the number of photons, we're going to say, and I'm going to let these equal this, the number of photons times the energy of one is equal to the energy total.
Mhm.
So that means the number of photons is equal to the energy total minus the energy of one. Now, for the problem where you're heating up the eyeball, the energy total would be equal to Cm delta T,
Mhm.
right?
Right.
But for this problem, we're not heating up the eyeball. We're just saying, hey, the eye gets this much energy.
Mhm.
Now, how do you calculate the energy of one? That's negative RHC over, excuse me. I'm thinking about a hydrogen atom, I'm sorry. So the energy of one photon, you're going to use H nu,
Right.
or HC over lambda,
Yeah, yeah.
and that's the energy of one photon.
Mhm.
So we know that H is 6.626 times 10 to the minus 24 joule, 34 joule seconds. C is 2.998 times 10 to the 8th meters per second. And in this case, you have 470 nanometers. So it's 470 times 10 to the minus 9 meters, right? Now, don't be fooled. If it says 470 times 10, if it says 470 centimeters, don't use 10 to the minus 9, right? What do you use?
10 to the minus 2.
10 to the minus 2. So be careful. Don't take anything for granted. Think about every little move you make. So here, that's 10 to the minus 9. Here, it's 10 to the minus 2. Don't take the exam in a, what would it be called? Where you just kind of do things automatically. Don't take the exam under automatic control. Think about every step you make. Okay, leave nothing to chance. Or that's the way I've always done it, because it may be a little bit different. Well, once you calculate this energy, you stick it in here and put that other energy, which was 2.5 times 10 to the minus 14 joules, and boom, you got your answer.
So is this the only other equation? Like you couldn't use the heat of fusion, the mass times the heat
Well,
of fusion for the total?
you could certainly do that if your eyeball was melting.
Right.
Now, that's a pretty gory problem. Your eyeball is at its melting temp.
But if
And
ice
it
is
absorbs
melting
this
to
much
water,
energy to completely melt. And the mass of your eyeball is this, and the heat of fusion of your eyeball is this. How much energy does it take to completely melt your eyeball? That's a nasty question.
okay, fair enough.
But that's kind of interesting. Now I may have to remake the exam and do a heat of fusion with your eyeball.
So the total energy is the kinetic energy plus the potential energy. So when the potential,
No, not in this case. The energy when you calculate it is heat energy, so that's kinetic.
but yeah, the potential energy is 0. There's
Yeah.
no potential.
Yeah, we're not really looking at any change in potential energy.
So you could also give us the kinetic energy of something and that could be the total.
Yeah, but you already know that I'm not going to give you any problems where I ask you to calculate any sort of work.
Right.
So,
And okay, yeah.
so we're going to be working simply with heat type of energy
Okay.
or energy due to transitions.
Transitions like phase changes.
No, I'm talking about transitions like orbit 5 to 2 or something
Oh,
like that.
yeah. Okay.
Or 2 to 5.
Mm-hmm. There was another one too, right at the beginning, Charlotte. It was like one of the first questions where the distance equals the wavelengths times the number, just like this one.
Oh, okay.
It was like one of the first questions, like how far away are you from the radio transmitter?
Well,
how many wavelengths in between?
I remember that.
if you want,
Really similar.
here's one kind of like the one you just asked about. Number 64, it's got a red triangle because it's supposed to be pretty hard. So red triangle is kind of like the radiation symbol, danger, danger. So exposure to high doses of microwaves can cause tissue damage. Examine how many photons with wavelength of 12 centimeters must be absorbed to raise the temperature of your eye by 3 degrees. This may be the problem you were referring to where the eyeball changes temp.
Mm-hmm.
Now, if your eyeball changes temp by 3 degrees Celsius, that is a radical change in temp. And it will cause damage. Your eye shouldn't change by more than maybe 1/10 of a degree Celsius at most.
Right.
Assume the mass of an eye is 11 grams and the specific heat capacity is 4 joules per gram K. So here we can still do this. Just to think about the problem and all of the parts of it. So this is number 64. We're going to piggyback and say that the number of photons times the energy of one is equal to the energy total. Right?
Right.
And therefore, we're going to use this equation. And the energy of one, we're going to use the H frequency, which is also HC over lambda. And for the energy total, that's going to equal the amount of heat that the eye absorbs. And that's going to be Cm delta T. And they give us the specific heat capacity as 4. They give us the mass as 11. And they give us the change in temp as presumably an increase of 3.0 degrees Celsius. So you can see just by looking at all of these numbers, you have 4 times 11 is 44, 44 times 3 is 132.
Mm-hmm.
And for the energy of one, since the wavelength is 12 centimeters, we would have 6.626 times 10 to the minus 34 joule seconds. 2.998 times 10 to the 8th meters per second. All of this divided by 12 times what?
10 to the minus 2.
10 to the minus 2 meters. And we could even estimate this answer, because we know that 6.6 times 2.9 is 20. 20 divided by 12 is 1.8. Or maybe 1.7, I don't know. Negative 34 and 8 is negative 26. The 2 comes up top, becomes positive 2, so we get times 10 to the negative 24.
Mm-hmm.
And then we plug that all in together and we get 1.8 times 10 to the minus 24 joules-ish, right? Because it's an estimate.
Right.
Oh, I got them in the wrong place, don't I?
Yeah.
132 joules.
But if we wanted to do per mole, we just multiply it by Avogadro's number, if you asked for that too.
Right, if you wanted Avogadro's number for this bottom number, but that's not what we're doing here. So you can see that 1.8 goes into 132 over 65 times. So we're going to call it 75 times. And then times 10 to the 24 photons. Does that seem like a lot? That's more than a mole of photons, right?
Yeah.
That's like 100 times bigger than a mole of photons. So it's going to take a lot of energy to change your eye by that temp.
Mm.
What's going to change the temperature of your eye faster? Longer wavelength photons or shorter wavelength photons?
The shorter is more energy.
Shorter is more energy. So this is really short, but compared to like 1 meter, right?
Mm-hmm.
But remember, if you have nanometers, if it was 12 times 10 to the minus 9 meters, so that's nanometers, this is really short, which means high energy, right?
Yeah.
So this is, like they say, this is a microwave.
Mm-hmm.
Microwave doesn't change your eye temperature as fast as visible light or infrared light or ultraviolet light or gamma rays or X-rays.
Mm-hmm.
So that's why microwaves take a lot of energy. Have you ever noticed, I don't know, the house that, our house, when you turn on the microwave, sometimes you get things dimming. Okay, anything else I can help you guys with?
We don't need to know about nodal services, do we?
No, you don't need to know about nodal services. I don't think that's an important topic for our level of class. But nodal surfaces are interesting because nodal surface is where you cannot find an electron. So your p orbitals actually have a nodal surface. So this is a 2p orbital, 2px. And this is your nodal surface. It's a plane.
Where there's
If I
like
draw-
zero probability.
What's that?
Is that where there's zero probability if we were looking at the limit?
That's right. You cannot find an electron in this plane, period.
Mm-hmm.
But the electron could be here or it could be here.
With any orientation, it's still at the origin. Oh, the X, Y, and Z for the P.
Yeah. So in the 2px orbital, you cannot find an electron in a plane that is like that.
Mm-hmm.
You can't find it in your ZY plane. So I want you to think about that. The electron is somewhere in this region, but it's never at the origin. So how does it get from one place to the other?
I don't think we know, do we?
What's that?
Do we know how? I mean, it just appears there.
Well, it turns out this is just a model,
Okay.
right?
That's the answer. That if we don't know, just
It's just a model. You can't find the electron in the origin because what is the origin?
the center,
And what is the center of an atom?
nucleus.
The nucleus. Do you
Yeah.
find electrons in the nucleus?
No.
No. So the most common answer is, well, the origin is the nucleus. You can't find electrons in the nucleus.
Right.
But still, how does it get from one side of the nucleus to the other side without going through the nucleus?
Hmm.
And the answer is this is just a model. Maybe the electron actually goes outside of the orbital for a little while to get to the other side, right?
Mm-hmm.
Besides, this is what we call the 90% boundary, right?
Yes.
So 10% of the time, where is it?
Outside.
It's outside that boundary, which means it can go around the nucleus, for goodness sakes. Don't get don't get all twisted up about it. It's just a model. You with me here?
Yeah.
So the way I used to sell this is I say that, it's really magic. The electron is everywhere simultaneously. So on a particle level, electrons are God because they're everywhere at the same time. You with me? So in these orbitals, they actually have these little churches. Where electrons are the center of everything. And you guys probably wonder, why does Easter start with an E? Because electrons are at the center of everything. That's the conspiracy theory I'm trying to start. I don't know if it'll take hold, but
Gosh.
there's always hope that someone's going to believe some sort of stupid thing like this. But again, it's just a model. And where is the 100% boundary for these electrons? The 100% boundary?
Infinity? The universe?
The universe. I would say
That
infinity.
equals infinity.
I would
right?
say infinity, but the universe is not infinite. So the 100% boundary is the universe. So could that electron have gone out somewhere in the universe and then come back here? You bet your bippy. Okay. So in response to your question, do we need to know about nodal surfaces? And the answer is no. But just so that you've asked and you might be interested, there's two types of nodal surfaces. There are planar nodal surfaces and there are spherical.
Okay.
And so if you look at a 3px orbital, it actually looks like this. Kind of like two peas and two lima beans. And this right here is a spherical node. So what does that mean about the electron that is somewhere in this region and it can never go through this sphere?
That's the nucleus.
No, the sphere is not a nucleus. The sphere is outside the nucleus. Here's the nucleus right here. This one is the one that's supposed to really make you wonder what's going on. You can't be in the sphere, but you can be in both places. I don't know. It is magic.
Mm-hmm.
And if this is what a 3px looks like, what does a 4px look like? It looks like this. This is a cutaway, of course, where you got one nodal surface here. That's a, this is called a spherical node. This is a spherical node. Plus you got the planar node.
So the 2p just has a planar?
The 2p only has a planar. The 3p has a planar and a spherical. The 4p has two spherical and one planar.
So then an S doesn't have any?
And a 1s has no nodes. A 2s has a spherical.
And the spherical, is that, what is,
It's a place where you can't find electrons.
if it's in the 2?
Yeah.
And is that the 1? Technically, is that within the 1 that you wouldn't find it? Should it be the same size as the 1s?
No.
Okay.
Nope. If you had to draw these two together, it would look kind of like this. Here's the 2 and here's the 1.
Okay.
So do you see why we don't usually draw subshells or orbitals together?
Mm-hmm.
Because they're complicated, right?
Yeah.
Okay.
So
But
we
you
don't
know,
have to overlap them or anything
Yeah.
on the exam.
so this is Charlotte's fault that she asked about nodes. But the number of nodes, but if you want to know the planar nodes for a subshell is equal to L is equal to L. And the number of spherical nodes for a subshell is equal to let me see if I'm getting this. Spherical nodes is equal to L. SPDF 0, 1, 2, 3. So the number of planar nodes is equal to the subshell. So like for a D, here's one plane and here's another plane. So you've got two planes. And the number of spherical nodes, you see here, you got one for a 2P. So the number of spherical nodes is equal to n minus 1. Okay. I've had enough. How about you guys?
Yeah.
If you want more, you can come back at 6.
Okay.
The Tony show will continue, and I will answer any questions you have about this material and try and help you understand it better. You should notice I sent out an announcement earlier today that you have a practice, if you will, exam so that you can open it up, see what the periodic table looks like, adjust your browser settings so that you can make that as big as possible. It's a different periodic table than we've had in the past. And the reason for the different periodic table,
That's good.
Because-
I looked at that.
because I want it to look like the book, where this starts with cerium and thorium. Our previous periodic table started with lanthanum and actinium.
Perfect.
And that might be important when you're trying to get the electron configuration based on the SPDF format. So I gave you a different periodic table to match what we've been doing in class. Okay. Since it's a different periodic table, you might want to open up the practice, if you will, exam so you can see what it looks like. And it's also there so you can submit a answer if you want, just to see what it's like to go through that process and find out if you're going to get kicked out for something. Actually, I take that back. On the practice exam, you can't submit anything. It's just so you can look at the periodic table. On the practice submission, you can submit something and see if you're going to get kicked out. And then ultimately, the only 2 things you need to open are exam 3 remotely proctored, because that has all the questions, but you can't submit anything. And there's exam 3 submissions remotely proctored, which you have to submit stuff. There's only 10 questions. They're worth 11 points each for 110 total. The questions actually say they're worth 10 points each, but when I grade them out of 11.
Right.
And usually I put 11 questions on there, but one of the questions I took off because I didn't like it and I didn't have enough energy to come up with a different question.
So there are only 10 questions this time?
Yep, 10 worth 11 each instead of 11 worth 10 each.
Oh, okay, 11 points each.
Yes, but on the exam, it's going to say it's worth 10 points.
Yeah.
But I graded out of 11. So if you get it 100% correct, instead of getting a 10, I'm going to write 11. Okay.
Okay.
So, and I'm not going to go in later today and come up. I do actually have a good idea for question 11, but I'm not going to do that because I'm too lazy.
But we still have the same amount of time allowed?
I think this time I gave you 180 minutes for the exam. So that's 3 hours.
Okay.
And you have 30 minutes to submit afterwards with the submission part.
Okay, so that doesn't include the
Do
submission.
we
That
need
does-
like graph paper or anything with our?
You know, you should always have graph paper at hand in case you need it.
Yeah.
It's just a nice thing to have. You should have your index card. Oh, now I realize I need to change the submission because I forgot to put a place down for your index card. So I have to add those. But I sent out an announcement about those 4 exams where 2 of them are kind of like a way for you to look at it beforehand and make sure you can do it with Proctorio. Kind of like I did last time. Some people took advantage of that, some people didn't. Fair enough?
Yep.
All righty. You all have a good afternoon. Try to enjoy the day. It's nice out here in Eureka. Hope it's nice where you are.
All right.
All right.
Thank you.
You
Thank
bet.
you. Have a good
Bye-bye.
day.
And Rebecca, I will start posting those other ones right now.
Oh, perfect. Yeah, I
Okay.
want to go back over them.
It'll probably take about half an hour for them to load into YouTube.
Okay,
Okay, bye-bye.
bye. Thank you.